Hello friends, in today's question, a rod A constrained to move in a vertical direction rests on a wedge B as in figure. Find the acceleration of rod A and wedge B instantaneously after the system is released from rest, neglecting friction at all contact surfaces. So this is a wedge B having a mass capital M and angle of inclination is theta, and this is rod A having a mass small m and it is constrained that is only going to move in one direction. Okay. So we are supposed to find out what will be the acceleration of A and B. First of all, let us say that wedge B moves towards left with an acceleration of capital A. Okay, this is a acceleration of, and we say that block A moves along the inclined plane with the acceleration of small a. Okay. So first of all, let's solve it for wedge, and then we are going to define the parameters for the rod. So let us draw all the forces that will be acting on this wedge. So this angle is given theta. So first of all, there will be mg acting in the downward direction, and we have acceleration A towards left, and there will be normal because of rod A in this direction. This will be n, and we can have this two components. So this will be our n cos of theta, and this will be n sine of theta, and there will be another normal because of this surface on which the wedge is resting, and let us call that as n prime. So we can write all the equations for this wedge. You can see that our n sine theta will be equal to mass into acceleration, and from here we can find out value of n. You can see that n is equal to ma divided by sine of theta, and let us call this as equation number 1, and second we can say that n prime minus n cos of theta and minus mg will be equal to 0, and let us call this as equation number 2. Now for rod, okay, you can see that rod A moves with an acceleration of small a. Okay, it moves with the acceleration of small a, and let us draw the rod in which we can show the direction of the acceleration also. So the rod will be something like this, and it is on the inclined plane. Okay. And you can say the force which will be acting will be mg in the downward direction, and there will be a normal because of the wedge that will be acting in this direction. We call this n, and this can be having two parts, components rather. Okay, so this will be theta, and we are going to have this as n cos of theta, and this will be over n sine of theta, and we are going to have acceleration a. This will be the direction of acceleration a. So we can also find out the equation of the motion for this wedge. We can say that mg minus n cos theta will be equal to ma, and we already know value of normal n, that is equation 1. Let us call this equation 3. We can say using equation 1 in equation 3 we get mg minus substituting value of n, that is ma, and from here we are going to add cos theta and divide by sin theta. Okay, and this will be equal to ma. Okay, now what we can do, we can find out the relationship between the acceleration of the wedge as well as the rod. Okay. So next will be the relationship between acceleration of wedge B and rod A. So in this case, you can say that if one body, or rather say one thing, moves by x distance, then we can say other body will be moving by y distance. Okay, so you can say that if the rod is displaced by vertically by y, the wedge moves through x. Okay, wedge moves through x. So basically it means that this rod travels a distance of y when wedge moves by a distance of x. Okay, it moves by a distance of x. So can represent this thing by using a triangle. You can say that it moves by distance x and rod moves by distance of y, and we have this angle of theta. So we can say that y is equal to x tan of theta. Okay, and if you double differentiate this equation, equation, let us call this as equation number 4. Double differentiating equation 4, we get A is equal to capital A tan of theta. By using this relation, we already know the equation. Let me write it again. We know that mg minus ma cos of theta divided by sin theta is equal to ma. So substituting value of acceleration, okay, let us call this as equation number 5. So using equation 5, we get mg minus ma cos of theta divided by sin theta will be equal to ma tangent of theta. Now this can be further solved as, you can write this as mg is equal to, taking a as common, we are left with m tangent of theta plus m cos of theta divided by sin theta. And from here we can find out, for the solve, taking tan theta as sin theta plus cos theta. So we can say that this can be written as a, we have m, taking sin theta as LCM also, so we have m sin square theta plus m cos theta divided by sin theta. So we get a as, a will be equal to missed one thing, sorry. This will be, let me do it again. So we can say that this a, we get this m sin theta oblique cos theta plus capital M cos theta oblique sin theta. I missed cos theta in the tangent part. And this, you can write this a, taking sin theta cos theta as LCM, this will sin theta multiply by cos theta. Okay, so we get m sin square theta plus capital M cos square theta, and this is equal to mg. Now we are going to simply cross multiply. We get a is equal to a will be equal to mg sin theta cos theta. A will be equal to mg sin theta cos theta, and divided by, we have m sin square theta plus capital M cos square theta. This is the acceleration of the wedge. Okay, we get this as acceleration of the wedge. I think the wedge was called as a wedge was called B. So we already derived from the relationship. Okay, we know that A is equal to A tangent of theta. So we put value of A, capital A rather, in this equation. So we get A is equal to mg sin theta cos theta into tangent theta divided by m sin square theta plus capital M cos square theta. Now tangent theta can be written as sin theta oblique cos theta. Okay, so we say that this is equal to mg sin theta cos theta divided by m sin square theta plus m cos square theta multiplied by sin theta oblique cos theta. So cos theta cancel with cos theta. So we get A is equal to mg sin square theta and we have m sin square theta plus capital M cos square theta. And if you want, we can further solve it. Okay, we can take sin square as, I think there is no need to solve it. If I'm not wrong, this is the correct one. Okay, yeah, looks good. So we have, this will be the acceleration of the rod A. Okay, so this completes the question. Thank you.